Okay. And that mic was going. Did we see movement? Yes, okay. So alternating series, that's where we're at. The most important thing when you're looking at this, you recognize that's an alternating series because you see the switch. You see, she is here. We see the -1 out in front there. So that tells us it's an alternating series. And when we're dealing with an alternating series, this piece right here, the a sub k, is positive. So that a sub k doesn't include the switch. All right, so normally up to this moment, we've been thinking of a sub k as representing the entire term, including its sign, if there was a negative. But now we're thinking of that as positive, and this is separate. So some important things when we're thinking about a series, we've talked about S sub n a million times. That's the partial sum, the nth partial sum. And if we have a series that converges, you can think of the partial sum as a bunch of leading terms, and then the remainder is what's the difference between S sub n and the actual sum of the series. So S sub n is the sum of the first n terms, and then the remainder is the sum of the tail. And I've mentioned, and we looked at an integral property that the remainder has last time. The only series we're really going to focus in on the remainder is this one. It's the alternating series because it turns out to be pretty easy. This is the estimate for the remainder of an alternating series. So what that says is all we need to do is look at the magnitude of the first unused term. That's what that says in yellow. Right, so we've got our remember that with an alternating series that converges, we're thinking about anytime we have a convergent series, whatever it converges to is like a horizontal asymptote. And so an alternating series, if it converges, is going to be above and then below. Your partial sums are going to be creeping closer and closer to this sum, to this asymptote. And so let's say S sub n happens to be positive. So the sum of the first n terms is positive. Then R sub n is going to be this positive distance right here between the actual sum of the series, which is in red, and that partial sum. Now, if you added the next term would be negative. Right? There's the next term, which would drop you down to S sub n plus 1. If you take S sub n and you add one more term, now we have S sub n plus 1. And isn't that green distance bigger than that black distance? Yes. And so this right here is an estimate for this remainder. This is the first unused term for that partial sum. That's going to be an estimate for the remainder. Then let's go to the next term. Let's add a sub n plus 1, which actually is a subtraction in this case, and it brings us down here. Now the remainder is here, and that's negative, right? Because to get from here up to here, we would be subtracting. And the first term that's unused after that moment is this one. It's going to bring us back up to this next partial sum. It's going to be positive. But once again, this green line is bigger than the black line. So the first unused term is always going to be a pretty decent estimate for the remainder. So we just have to look at the first unused term. So it's a lot easier than looking at those integrals that we had on the board on Thursday that the remainder is trapped in between. In higher level courses, you'll look at those integrals in detail. In this class, we want to focus on the remainder just for this type of series because it is very visual and you can kind of grasp it more intuitively. So let's try a couple. So these are two convergent alternating series. We see that they're alternating because they have a switch. The a sub n here is 1 over k. The a sub n here is 1 over 2k plus 1. So again, the a sub k does not include the switch. Both of these converge, and we know what they converge to. That's not really important what they converge to in this case. It's just what we just happen to know in these two. Okay, so this says how many terms of the following convergent series must be summed to have a remainder less than 10 to the negative 4. So we want to know when this a sub k is going to be less than 10 to the negative 4. Okay? So if we can go out in the series and we can find the very first term that's less than 10 to the negative 4, we add everything in front of it, because that term will represent the remainder value that we're looking for. All right, so if we're adding up all these terms, the first term that's less than 10 to the negative 4, that will be the remainder for everything in front of it added together. So that's what we want to find. We want to find, hey, where's the first term in this series that has that? So if we think about our terms generically here, when we plug in a 1 up here, it's going to be positive. So the first term is positive. So I'm going to call this a sub 1, and then the next term is going to be negative a sub 2. The a's are positive, but there will be negative signs. So it's going to look like this if we keep on trucking. Now, when we get down to, we get further into the weeds here, let's call this a sub n minus 1, and then a sub n, and then a sub n plus 1, etc. Now, I don't know exactly where the minuses are, right? I don't know if n is even or if n is odd. So if I just choose, and it's all going to depend on the problem if we really were trying to be specific, but these signs are going to be alternating. It doesn't really matter whether it's minus plus minus or plus minus plus. They're alternating. As soon as we can find the first term that is less than 10 to the negative 4, we just add everything in front of it. Okay? So let's figure out which term is going to be the first term. All right, so this is an inequality. We know how to solve inequalities. Let's rewrite this as a fraction on the right-hand side, so 1 over 10,000. Let's multiply both sides by the least common multiple. Cross-multiply is another way to say it. So k has to be greater than 10,000. What is the first integer greater than 10,000? 10,001, exactly. So now I'm going to come back up here and let's re-envision what's happening here. So let's change these subscripts now that we have an idea of what the k value should be. So when k is 10,001, first off, that's an odd number, and the odd indices should have pluses. So we're coming down here. The odd indices should have pluses. So let's make this, I'm going to make that a minus. I'm going to make this a plus. So a minus, a plus, and then this would be a minus. And so 10,001, so I'm going to call this a sub 10,001. This would be a sub 10,002. This would be a sub 10,000. Right there. Everyone tracking? So when we plug in 1 or any odd number, we'll have a plus in front of that term. Right? We plug in a 1, we get 2 up there, so that's positive. Now this tells us that the first a that has a magnitude less than 10 to the negative 4 is when k is 10,001. That's an odd number, so it's also going to have a plus in front of it. So this term right here, maybe I won't try to maybe I'll highlight it. So that term right there is less than 10 to the negative 4. That's the first term that's less than 10 to the negative 4. So that is going to mean that we want to add up all of these. So we're going to add those. We're going to sum all of those. And this term right here is going to be the remainder. Make sense? So S sub, this is the sum of how many terms? The blue there. 10,000. We start at 1 and go up to 10,000. So S sub 10,000. that is going to be the sum from k equals 1 to 10,000 of this. So this is the partial sum that we want. We want 10,000 terms. So that is our answer, 10,000 terms, and here's how we would write the partial sum. But the answer is we want 10,000 terms. The 10,000 in first term is the remainder for everything that's in front of it added together. So what this means in words, you could say this. You could say S sub 10,000 is within 10 to the negative 4 of what it converges to, of natural log of 2. So that's how you should be thinking of it. So if we know that the limit is natural log of 2, we're going to be within 10 to the negative 4 of that if we add up the first 10,000 terms. So this is the minimum number of terms that we add together to be within 10 to the negative 4 of the sum of the series. Well, let's try another one. These are definitely a little tricky. So notice that this one starts at 0. So we're going to have to deal with that counting issue where we're shifting things around. So let's see. So let's take our a sub k. Our a sub k does not include the switch. So there's our a sub k. We want it to be less than 10 to the negative 4. So that's the inequality we need to solve. So we solve this inequality by cross multiplying. We're going to have 10,000. And we're going to have 2k plus 1 on the right. Subtract 1, and we get 900. We get that number. 9,999. And then we divide by 2. And we need to figure out the first k. K is an integer, positive integer. We want to know the first k that satisfies that. And what would that k be? If you plug that into your calculator, you're going to get, what's that first k going to be? What's the first integer bigger than that? Well, so 10,000 divided by 2 is 5,000. So is it going to be 5,000, 4,999, or 5,001? What's it going to be? Type it in your calculator and look at the number. And what's the first integer bigger than it?
5,000.
5,000, exactly. 5,000. So that means that when k is 5,000, the magnitude of that term is less than 10 to the negative 4. So we want to add everything in front of it. All right. So if we think generically about our summation here, if we think generically, this first term is going to be an a sub 0, and it's going to be positive. And then it's going to be minus a sub 1, and then plus a sub 2, minus etc. When we get to a sub 5,000, so a sub 5,000, should there be a plus or a minus in front of a sub 5,000? Plus, because all the evens have a plus. So there's going to be a minus on the next term, which will be a sub 5001 plus etc. There will be a minus before, so that's a 4,999. So there's where we're at. So now this term is the first term that's less than 10 to the negative 4. The first term that's less than 10 to the negative 4 is when k, the index, is 5,000. So we want to add everything in front of it. So we want to add up all of those. So as soon as we find the term that's less than the prescribed error, we add up everything in front of it. So how many terms is this?
5,000.
5,000 terms. Because this started at 0 and ended at 4,999. So this is S sub 5,000. S sub 5,000 is within 10 to the negative 4 of pi over 4. Because this series converges to pi over 4. So we're within 10 to the negative 4 of pi over 4. So same process up here. Whatever the term is that's our first term that's less than our error threshold, we add up everything in front of it. This one started at 1 and ended at 10,000, so that's 10,000 terms. This started at 0 and ended at 4,999, so that's 5,000 terms. Okay. Now, this is the alternating harmonic right here. Right, that's the alternating harmonic. Let's put to words, just note, let's just put some words to this just to make sure we're sort of getting it. So the alternating harmonic, natural log of 2 is equal to 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, etc. And that converges to natural log of 2. So let's put some words here. If we add these two up, that would be called S sub 2, correct? Sum of the first two terms. How much is S sub 2, or what's the value of S sub 2? 1/2. 1/2 is within how much of natural log of 2?
Whatever the remainder is. It's within 1/3.
1/3. It's the first unused term. First unused term is the measure of the remainder. If we go to S sub 3, that's going to be 1/2 plus a third, which is 3, 4, 5 over 6, I believe. That's going to be within how much of natural log of 2? 1/4.
Because it's absolute value.
Yep. It's always the magnitude of the first unused term, so that it's always going to be a positive number. So if we went to S sub 4, I'm not going to add it up, but this is going to be 5 over 6 minus 1 over 4, whatever that happens to be. That's going to be within how much of natural log of 2? 1/5, exactly. So the first unused term gives you error on adding everything in front of it. The terms that lead up to it. Add all those up, and you'll be within that unused term value of whatever your error is. So not too crazy. Come on, there we go. So let's try another one here. So this one converges to pi squared over 12. We don't really care about the pi squared over 12. We're just looking here. We see that it's alternating. We identify A sub k. A sub k is everything but the switch. So there's A sub k. We want to know how many terms do we have to add up to be within 10 to the negative 4 of this pi squared over 12 thing. So we don't even need to know that it's pi squared over 12. We just need to know that it converges. So we want to be within 10 to the negative 4. So we want this to be less than 1 over 10,000. We cross multiply. And we want to know the first k value that satisfies this. What is the first k value that satisfies that? $101. 100 squared is 10,000. So the first k value that satisfies k squared being bigger, not equal to, but bigger is that. So now we start looking at this expansion here to get, we don't have to look at the expansion, but it gives you a pretty decent visual. The first term here is going to be A sub 1, and it's going to have a positive in front of it, because if you plug in a 1, you get an even exponent, so that's positive. And then it's going to be minus, and then plus, and then minus, etc. And then we're going to get all the way down here to A sub, let's put a term before it, and a term after it. So we have this kind of thing. Should the a sub 100 be positive or negative in front of it?
Negative.
Negative, because all the evens will have a negative. If you plug in an even up here and add 1, you get an odd, which will preserve the minus. So that even will have a negative, this even will have a negative, then we'll go plus dot dot dot, and this odd will have a positive. And then we say, okay, 101, k being 101, this term is the first term less than 10 to the negative 4. So we want to add everything in front of it. So we're going to add those. How many terms is that?
Uh, 99, 100.
Final answer? 100. Final answer. Right? This one started at 1. So whatever that index is down there, that actually is counting the terms. So that's going to be 100 terms. So we could say that S sub 100 is within 10 to the negative 4 of, we happen to know what the limit is, or what the sum is in this case. So we're within 10 to the negative 4 of pi squared over 12. All right, you all try this one. See if you can figure out how many terms we have to add up to be within 10 to the negative 4 of pi cubed over 32.
To what magnitude?
Say again?
To where?
10 to the negative 4, so within 10 to the negative 4 of that limit, or of that sum. Anyone get their K value yet? What'd you get, Daniel?
11.
11. Let's go that far at least. So we cross multiply. You take the third root of both sides. And when you take the third root of 10,000, what do you get to the nearest decimal, one decimal place?
21.5.
21.5. So we need to be bigger than 21.5. So that tells us that if we subtract 1, or we could even go all the way before we do the approximation. It really, there's a couple ways you could do it. You could take the third root of 10,000 and then subtract 1 and then divide by 2. So you could go all the way to here if you prefer. And then we just type that in the calculator, make sure that the numerator is in parentheses so that we're dividing 2 into that entire quantity in the numerator. And then this tells us, did you all get k equals 11?
Yeah.
So k equals 11. So then we want to create a visual. You don't have to create your visual up here, but I find it very helpful. The first term is going to be a sub 0. That'll be positive. If you plug in a 0 up there, that's positive. And then minus a sub 1 plus a sub 2 minus a sub 3 plus etc. And then we're going to have a sub, usually we want to do term before, term after. Let's see. So where should the plus go? And should we have a plus in front of the a sub 10 or a minus?
Plus.
Plus because the evens have positives, so positive, positive, minus etc., and that will be a minus there. So when k is 11, so we're looking at this piece, we're not including the minus sign, this is less than 10 to the negative 4. So that tells us that we want to add everything in front of it. So we're going to add those. And how many terms is that? 11 terms. We started counting at 0, and we ended counting at 10. So 0, so if you include 0 and 10, that's 11 terms. So we're going to have 11 terms that get added together. So that means S sub 11. Right? S sub 11 means the sum of the first 11 terms. S sub 11 is within 10 to the negative 4 of whatever the limit is, pi cubed over 32. Now, if you didn't know what it converged to, we would just call that S. We would just call that capital S. Right, capital S with no index, no subscript, is the sum of the series if it converges. So if we didn't know what this value was and we just knew it was a convergent alternating series, we would just say within 10 to the negative 4 of S. So also notice that all these alternating series obviously converge. So with the alternating series test, there's only 2 steps. Take away the switch. The limit of this has to be 0. And the terms have to be decreasing. These terms here that are all positive have to be decreasing. 1 over k squared, you can visualize 1 over x squared, right? That's a decreasing function. As k increases, the denominator is increasing, so the fraction is shrinking. And that's true for all these. When you look at your a sub k here, the limit is 0 as k goes to infinity. And if you go from k to k plus 1, if you replace that k with the k plus 1, you've increased the denominator, so you've shrunk the fraction. So they're all decreasing to 0, which means they're converging. Decreasing to 0 means they converge when you take away the switch. If you take away the switch and it decreases to 0, it's going to converge as an alternating series. So, when you have an alternating series that converges, there are 2 classifications of that convergence. That convergence can either be absolute or conditional. So let's look down here for a second at the flow chart. Now here, this is a little more generic than alternating series. Like, it's not saying alternating series. When we specifically have a series that goes plus minus, plus minus, plus minus, it's called alternating. If it just goes, if it has some minuses in there, but they're not that systematic, if it's plus, 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 minus, minus, plus, plus, minus, plus, 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 if it's all random, then it's not an alternating series, it's a series that has positive and negative terms. So here, this a sub k is not necessarily positive. This is just saying generic a sub k. It's a series that could have minuses in it, but it's not as specific as an alternate. It's not as regimented as an alternating series. So it could have groups of minuses in places. All right, so that's what we're thinking of here. Just a series that has positive and negative terms. Converges or diverges. If it diverges, you're done. If it's convergent, then you can classify the convergence as either absolute or conditional. All right, so what do those mean? All right. So first thing, if you see this absolute value right here around the a sub k, now we're making all the terms positive. So this is saying if you take the sum of absolute values and you get convergence, then we say the series without the absolute values, just the series that you're handed, this summation a sub k, we say that it converges absolutely. So if you've got your series and you take absolute values and you get convergence, it converges absolutely because you put absolute values in there and you got convergence, so it's going to be called absolute convergence. If you put in the absolute values and you get divergence, but the series without the absolute value converges, then the convergence is called conditional. We'll look at some examples because it sounds more complicated than it is. Theorem that we won't use that much, but hopefully will make sense. If a series converges absolutely, that means you put in the absolute values and you got convergence. If you take away the absolute values, the thing must still converge. Because the absolute values make the magnitudes all added together, right? There's no subtraction. If you make it all positive, if you force all the terms to be positive and you add it up and you get convergence, well, if you sprinkle some minuses in, that's only going to make it sort of converge to a smaller number. But it's still going to converge. Right? The worst case scenario is if everything's positive, and if everything is positive and it converges, if you sprinkle in some minuses, it's got to still converge. All right? So that's what this says. And the contrapositive of that says if you have a series that diverges, if you put in the absolute values, it still diverges because you're making it worse. Because everything's now positive, so that's going to be the biggest the possible sum could be. So let's look at a couple examples and try to wrap our heads around this. So this is an alternating series. For us to create series that just have random minuses sprinkled in there is a pain in the neck. You'd have to have a piecewise defined thing. Or you'd have to use a trig function that could somehow do something funky. So for us, we're thinking of these as alternating. Those are the easiest types of series that have alternating signs in them, is when they're in there systematically. So we've got this series here. It's got some minuses. Yes, it says it is an alternating series, but the more important thing is that it's got some minuses. And we want to analyze the absolute values, and then we also want to analyze the series as it is. Doesn't matter which order we do it in. Let's do the absolute values first, because that tends to be a little easier. So the series of absolute values means this series right here. We just take away the minuses. So in this case, we take away the switch. So that is the series of absolute values. Let me maybe even write that out in front right here. Let's write this as the series of absolute a sub k. K starts at 1. So if we make everything, there's just so many little nuances. When we talk about this as an alternating series, the a sub k doesn't include the minus. But if we talk about it just as a generic series that has some minuses, then the a sub k does include the minus. So we've got to be just a little careful with the minus thing. But here I'm implying that we're just making everything positive. If we make everything positive, we have that. And what kind of series is that? P series. So we say arrow, P is equal to 2/3. And then we compare that to what number? 1. So we compare that to 1 and then we make our conclusion. Converge or diverge? So for a P series, bigger than 1 is converging, otherwise you diverge for a P series. Bigger than 1 converges. Okay, so that tells us that the series of absolute values diverges. Now let's do the series as it is. So we're going to use the alternating series test because this is an alternating series. So we have 2 pieces to the alternating series. First piece says take the limit. And when you're treating it as an alternating series, you're just taking the limit of the sum and without the switch. And what is the limit of the sum and without the switch? 0. Right? Denominator is going to infinity. Top is a constant, so the values are going to 0. So that's first step. Second step, we want to show that the terms are decreasing. So we want to show that as we go further out in the series, we have that inequality holding. And here again, when we're in the alternating series test and we write a sub k, the a sub k doesn't include the switch. So we want to show that that's true. So a sub k is going to be 1 over k to the 2/3. We want to test this. And intuitively, we know that this is going to be true because there's nothing in the numerator. If the denominator gets bigger, the fractions get smaller. And we know it's going to be true. But we have to do the math. So we cross multiply here. Don't know quite. We don't know, but we do know kind of thing. So we have that. Raise both sides to the 3/2 power. So raise both sides to the 3/2 power, we get this. Subtract off the k, we can almost always get down to this numerical inequality that we can solve by inspection. That is true. So this tells us, because that's true, the series converges. So the series with the minuses converges. But if we take away the minuses, we have divergence. So now we can classify that convergence as what type of convergence?
Conditional.
Conditional. So therefore, conditional convergence. So it's conditional. You have to have the minuses to get convergence. If you take away the minuses and you still get convergence, it's absolute. It's really converging. But if you take away the minuses and you get divergence, that means you really need those minuses. Okay? Let's take a look at this one. This one is an alternating series also. Let's first consider the series of absolute values just to sort of get us oriented here. And again, it doesn't matter whether you do it the series of absolute values first or the series as it is first. Does not matter. So here is the series of absolute values. So the series of absolute values, we will have a 1/3 in here. We're taking away the switch. Okay, we'll start at 1. Okay, what kind of series is that?
Geometric.
That's a geometric series. So we identify what letter?
R.
R. So R will be 1/3. We compare it to 1. That is smaller than 1. What is our conclusion? Converge. So remember that for a p series, less than 1 diverges, but for a geometric series, less than 1 converges. And for a geometric series, you're focusing up in the numerator. Whereas for a p series, you're down in the denominator. So bigger than 1 in the denominator for that exponent is going to converge, but less than 1 is going to diverge. All right. Now let's consider the series as it is. So this series as it is. Probably should have given myself a little more space, but that's okay. What type of series is that?
Alternating.
It is alternating, but it is a special series. Special, we're geometric, telescoping, p series.
Is it geometric?
It's geometric. That is geometric. What's this R value?
Negative.
Negative 1/3. Right? For a geometric series, your common ratio could be positive or negative. And then we look at the absolute value of the common ratio, which is 1/3, and that's less than 1. Therefore,
Convergence.
converges. Okay. So this convergence is the one we're classifying right there. This convergence, is it absolute or is it conditional?
Absolute. Absolute.
Absolute. Okay. Now, we did this step first, and we got that the series of absolute values converges. So if you were super nerdy, mathy, you could say, oh, if the series of absolute values converges, that theorem that we just had, then it should have regular convergence also. If the series of absolute values converges and you take away the absolute values and you throw in some minuses, that still has to converge. So you could use that theorem. We're not going to use that theorem, but you could. I want to see both. So the series as it is converges because it's a geometric series with an R value of negative 1/3, which has a magnitude less than 1, so it has regular convergence. And then if we take the absolute values, we still get convergence, then the original convergence is called absolute convergence. Because it doesn't matter. You put the minuses in or you take the minuses out, you still have convergence. So it's absolute convergence. Now, when we have an alternating series, and so one point of clarification, we've seen that you can have an alternating series that's built with a switch, or that's built with a geometric series that's got the negative ratio. So you could go back and you could treat that last one as a geometric series or as an alternating series. You could do it either way. It's easiest if you treat it as a geometric series because we know if the common ratio has a magnitude less than 1, it converges. But you could treat it as an alternating series and not identify it as geometric, and it would still work. So this one is alternating. Normally, if we were going to prove an alternating series converges, we would normally do our two tests, right? Limit and then decreasing. And we do have to do that here, but the problem is to show a sub k plus 1 is smaller than a sub k is very difficult with this inequality here, with the square root. It'd be very hard to show. There is a way using Calc 1 to show that a function or a sequence decreases, and what is that?
The derivative.
The derivative, first derivative test. If you take the derivative of a function and it's negative, the function's decreasing, right? The slope of the tangent line is negative, that function must be decreasing, all right? So we could, if the a sub k plus 1 and a sub k, we can't get the inequality to be easy, which it won't be easy here. You can try it if you don't believe me. So we could use calculus and show that that function is decreasing. So there's another nuance here, though. One more wrinkle. You should have talked about this perhaps in Calc 1. Maybe not. Depends on your Calc 1 teacher. Depends on how thorough they can be, because it all depends on how things go in a class. Sometimes you talk about more than other classes. So that's square root. If we're going to use the first derivative test, we're going to be taking derivatives with square roots, which makes anyone squirm. If you're going to do the quotient rule and there's a square root in the bottom, you're doing low d high minus high d low over low squared. Square root's a pain in the neck. Do you see that this is true? Do you see in your mind that if the square of a function is decreasing and all the terms are positive, the unsquare of the function is also decreasing?
Sure.
If the square of a function is decreasing, we can think of it as continuous, like 1 over x squared. And then take away the square, 1 over x. If the square of a function is decreasing, the unsquare of the function is decreasing. So in other words, if you have all positives, if you have that this is true, this tells us that this is true. If everything is positive, A and B are positive. So let's call them positive reals. All right, that is true. You can test it, you can look it up, you can find a proof. It's very easy to prove. That you can subtract this over to the left and factor it and use the difference of squares argument and see that A minus B is positive, so then you add B to both sides, you get A is greater than B. So that'll be true. And the point here is this. Let's define the function g to be the square of this. Let's square this function because it's going to be a heck of a lot easier to determine whether this function is decreasing or not, because that function is going to be way easier. And I put in x here So I should either make everything x or everything k. I'll just make this a k. Technically, k means discrete, and you shouldn't be taking derivatives of discrete, but we get a little sloppy in most of these books when we do this. But that's going to be a lot easier to take the derivative of, because there's no square root. So let's find the derivative. So g prime of k. The low d high is going to be much easier here. There's low. D high is 4k cubed. Minus high is k to the 4th. D low is 6k to the 5. All divided by low squared. Everyone okay with that? Whoops. So then we just have to combine the like terms in the numerator. And what are we trying to show this is? What are we trying to show? Yeah, we're trying to show that this is negative. If the derivative is always negative, that means if the derivative is always negative, that means your function is decreasing. Okay, let's come up here and okay, we get negative 2k to the 9 plus 4k cubed, all divided by k to the 9 plus 1 quantity squared. Okay, do you agree the denominator is always positive?
How did the denominator become k to the 9?
Yeah, that's a great question. That is a great question. Thank you. Good catch. Do we agree the denominator is positive? Yeah?
Yeah.
Right. So that's not going to affect the sign of this function that we're calling g. Do you agree that the numerator is eventually negative?
Yeah.
Right? Because that k to the 9 dominates the k cubed. So the k to the 9 dominates that whole expression. And when you look at the graphs of powers, let's just look at graphs of powers of x for a minute. If you look at x squared, and we just look at the positive, x squared is that. And x cubed does this thing right here. Right? So the higher power eventually takes over. And that transition point is at 1. Right? The higher power is going to be below. When you're in the interval 0 to 1, it's below. But as soon as you get past 1, goes up. So this is not true for k equals 1 necessarily, which it isn't if you plug in k equals 1. But if you plug in k equals 2 and beyond, it is true. So when we're talking, you may say, oh, but this starts at 1, so this is not true for every k. It's true it's not true for every k. But it's true for all k beyond a finite number of k. So it's eventually true. So this is less than 0 for k greater than or equal to 2. Yeah, less than 0. So that means that the function, therefore, the sequence is eventually decreasing. Or you could say it's decreasing for k greater than or equal to 2. So that is the second part of our alternating series test, although we did it first. Well, let's call this 2. And then 1, the limit of a sub k as k goes to infinity. This is the divergence test part of it. We usually do this first. I was excited to do the calculus 1 thing. Not sure why. And you agree that that limit is 0? How would you prove that that's 0? It's not quite as obvious. Our technique would be to actually do something very similar. if you square top and bottom and pull the square root out like that, you agree those are equivalent?
Yeah.
Right? Those are equivalent? If you take the square root of k to the 4, you get k squared, and take the square root of the denominator, you get that. And then, if you're being really nerdy, you push the limit to the inside. And the limit of this is 0 because the dominant k power is in the denominator. We could divide by everything by k to the 4th. If you want to really keep on doing every gory detail, you could divide everything by k to the 4th. And we get to that spot there where we should be very clear that that limit is 0. This little fraction is going to 0. 1 over k squared goes to 0. The square root of 0 is 0. So that's how you would prove it. So now that we've done both things, we've checked that it's decreasing and we've checked that the limit of a sub k is 0. Therefore, we have convergence by alternating series test. I'll just put that in there just to make sure it's clear that's how we did it. Okay? So that tells us that the series as is presented converges. So we now have an alternating series that converges. That's what we just showed. It was a lot more work than the normal alternating series test has been. So now we need to classify that alternating series convergence. So our second part is now we're going to consider the series of absolute values. So this generic expression here is supposed to mean take absolute values of everything. It starts at 1. So when we look at the series of absolute values, we just take away that switch. So we get k squared over the square root of k to the 6 plus 1. All right. Anyone want to venture a guess as to how we analyze that series convergence or divergence?
Direct comparison test?
Direct comparison test. If you have an a sub k, and we're looking at it, we go through that triage process. It's not one of our special series. It's not a P series. It's not a telescoping series. It's not a geometric series. One thing you sort of hopefully are noticing is that we're adding 1. Adding 1 is insignificant in almost every series we deal with. And if you take away that plus 1 down there, you can simplify the square root of k to the 6. That's going to be k to the 3. And then you can simplify k to the 2 over k to the 3. And what should this series be behaving like? The harmonic. So our b sub k, we are choosing b sub k. First we ditch the insignificant term, the plus 1. And then we simplify all this. This is going to be k squared over k cubed. That's 1 over k. So that means that we're comparing it to the harmonic. And the harmonic diverges, and you can say it in one of two ways. You can say it's harmonic, therefore it diverges. Or you could say p equals 1, and p equals 1 is going to cause it to diverge. What should the inequality thing be here? Less than or equal to 1, therefore diverge. Or you could say p equals 1, harmonic, diverge. Doesn't matter. You could write this also. P equals 1, harmonic, therefore diverge. Either way, does not matter. Somehow you just have to indicate that it's the harmonic or that it's a p series where p is bad. Okay. So this comparison series that we're choosing diverges. So what do we suspect happens to the original series without that minus 1? This series right here? It probably also diverges. So let's see. Can we show it? So we would want to show the following inequality. So we're going to compare a sub k to b sub k. Do we want the a sub k, which is this original up here? That's going to be the a sub k that I'm talking about right here. That's a sub k for this analysis. Do we want to show that that's bigger than b sub k or less than b sub k? Bigger, because our two principles are bigger than diverging must diverge, and smaller than converging must converge. So if our b sub k series diverges, we suspect our a sub k series also diverges, and to prove that the a sub k series diverges, we can show that the a's are bigger than the b's. If the a's are bigger than the b's, the a series must diverge also, because bigger than diverging diverges. So let's see if we can do this. So we have k squared over the square root of k to the 6 plus 1. Is it less than, excuse me, is it greater than 1 over k? All right. Well, let's do our cross multiplication thing. We're going to have k cubed on the left. And then on the right, when we cross multiply, we have the square root of k to the 6 plus 1. Now we're going to square both sides. We get this. We get 0 greater than 1. True or false? False. So when we go to the comparison test, we try direct comparison first. If our inequality doesn't hold, we go for limit comparison test. So we always want to try the direct comparison first. Now, if we used a little bit of foresight, we might have been able to see that, oh, this might not work. Maybe we should go directly to limit comparison. What do you think? Can you see it before you do all the math here? When you look at this denominator here, when we took away the 1, this denominator here, this one, we decreased this denominator, so we increased this fraction value. So that tells us that the b's are actually bigger than the a's if we used a little intuition ahead of time. On the test, I'm going to ask you to do the direct comparison, and if it doesn't work, you have to do, then you go to limit. So it's all fine. So now we go to limit comparison test. And we take the limit of a sub k over b sub k as k goes to infinity. So this will be the limit of a sub k, that thing right there, square root k to the 6 plus 1. And if you divide by b sub k, that's the same as multiplying by the reciprocal of b sub k. So now we have this limit, which we actually already looked at just a second ago. Or at least we looked at a limit similar to this. What do you think this limit's going to be? 1. So if the way we analyze it would be to pull the square root and make it big by squaring the numerator. And then the limit jumps to the inside. The powers of k match. So that limit will be 1. So now we need to know, the most important thing with all these tests, we get all these numbers. We get a p-value of 1. What does it mean? We get, the other one, we got an r value. What does it mean? Here we get this limit for the limit comparison test. What does it mean?
It's in the set of all positive reals, so it converges.
So this
it does
is
the same thing as the
So it does the same thing.
as the b sub k.
Yes. So the two series do the same thing. They either both converge or both diverge. If that limit of the ratio is a number, that sort of means that they're linked together and they're sort of dragging through together. They're doing the same thing. Whether they're dragging to divergence or dragging to convergence, they're doing the same thing. So therefore, converge or diverge?
Diverge.
So both are diverging. So both are diverging. We chose a b sub k that diverges. That means that this a sub k series is doing the same thing, so it also diverges. All right. So our big conclusion then is what? So we have a convergent alternating series. When we took away the switch, we got divergence. So that convergence that we got is classified as conditional convergence. So in other words, we went through all that work to come to the conclusion that the minuses were very necessary in order to get that convergence. That's what that tells us. All right, I think it's time for a break. We'll just do it. Let's take 10. Take 10. Or at least my last alternating series problem. You all still have a bunch of them to do with homework. Okay, so we've got this alternating series. Let's go the other direction this time, and let's first analyze the series as it is, and then we'll analyze the series of absolute values. Doesn't matter which order you do it in. So this series is an alternating series, so we're going to use the alternating series test. It's not an alternating series that happens to be geometric that we could use the geometric series information. So we're going to use alternating series test. The first step is to take the limit of a sub k, and when you're treating it as an alternating series, a sub k doesn't include the switch. And what is that limit? 0. The denominators are getting bigger, fractions are getting smaller. So that's the basic limit. And then we have to show that the function is decreasing. The sequence of terms is decreasing. So we want to show that a sub k plus 1 is less than a sub k. So as we go out in the series, the terms are getting closer to 0. And this one we don't need calculus, or we could use calculus if we wanted, but we don't need to. So a sub k is natural log of k in the denominator. So 1 over natural log of k. We want to show that this is true. Cross multiply. And then what's our next step? Yeah, we're going to exponentiate. So when you exponentiate both sides, you get, you do what you said or what you were at least thinking. So you get to that. And then if we subtract the k, we get to our numerical inequality that we can solve by inspection. And that is true. So now we've got both pieces of the alternating series test checked out. So our conclusion here is that therefore we have convergence. So this is regular old convergence. We treated each term as it's given to us. We didn't modify anything. So now we decide whether that convergence is absolute or whether it's conditional. So that convergence includes the minuses. So now we're going to consider the series that has no minuses. So we're going to consider the series of absolute values, that series. And we did this series on last week on Thursday, or maybe it was Tuesday. And we did it with the comparison test. So when you look at this, there's not an obvious b sub k that we've generated in the normal way, take away the adding of 1 or take away something that's obviously insignificant. But what we did was we chose the b sub k to be 1 over k for the following reason. We know that 1 over k is a divergent series, it's harmonic. These denominators are going to infinity slower than just k. So these fractions are going to 0, but they're going to 0 even slower than this. So the harmonic is a good threshold series that if we can show something is going, the terms are going to 0 slower than the harmonic, then that series must also diverge. So that's our concept. So here, this is the harmonic. And this is a p equals 1, which is harmonic, therefore diverge. So harmonic. So we have that comparison series that diverges. So if we try the direct comparison, we want to show that the A's are bigger than the B's, because bigger than diverging will diverge. So that's what we would like to show. Will we be able to? Let's see. So the A sub k is 1 over ln k. The B's we said are the harmonic. So this is going to be k. We're going to get that. And so this is one that what we talked about, I'll mention it again, is that there's no real math that we can do that's super simple right there. If we look at the graph, though, there's a graph of y equals ln x, and here's a graph of y equals x. We just sort of know this as a basic fact that the identity function, y equals x is called the identity function, it's always bigger than the natural log function. So this is always going to be true. And we can see that we can see that x is always bigger than ln x. If you're in Calc 1 and you wanted to prove it, you would look right here. This is going to be the closest those functions ever are. And you would define a function that measures the difference. And then you would show that that difference is increasing. And that will prove to you that k is always bigger than ln k. So this is true. So this right here is true. And so now we have that direct comparison. If we get that this is true, and our B sub k series diverges, then our A sub k diverges also. Our A sub k series diverges. So therefore, we get divergence. And now we can come back up here and say, OK, well, that divergence means that this convergence is absolute or conditional? Conditional. So that has to be conditional. In other words, we need the minuses. If we take away the minuses, we get divergence. We need the minuses for convergence. All right. Alternating series, done. The next section, most find the next section one of the easier sections in all of Chapter 10. We are going to cover 2 tests in the next section. And the 2 tests that we're covering are important because, and the section's not that long, are important because in the following chapter, when we get to power series, the root and the ratio tests are going to be how we analyze power series. So I'll make one comment about power series. So these series that we've been dealing with are series of numbers. Right? We either have a bunch of positive numbers added together, or a bunch of positives and negatives added together. But it's just numbers. There's no variable. Right? The k is just a counter. It's not a variable. It just allows us to list all the terms. Then we add them all up. In Chapter 11, we put a variable into the mix. And we have something called a power series, which is a series of powers of x. And every single value of x creates an infinite series. So instead of just one infinite series of numbers, one little infinite series of numbers, now every single x that you put in generates its own infinite series. So you have this monstrous pincushion where every x you put in creates an infinite series. And then you have to figure out, well, which of those infinite series converge and which diverge. Because some of the x's will cause convergence and some of the x's will cause divergence. So that's where we're going, where every single x value is going to create a series of its own. Well, it turns out that when we get to those power series, these are going to be the two most important tests, the ratio and the root test. These will be the tests that you take forward into differential equations. These two tests are the ones that are the most common when you get to the generalization of a series, which is a power series. Okay. Now, these two tests most folks find pretty easy overall because the conclusions are identical to the geometric series. So remember with the geometric series, ratio less than 1 converge, ratio greater than 1 diverged. The one extra caveat here is that if r is 1, the test is inconclusive and you have to try a different test. So the ratio and the root test are going to have the same exact conclusions here. Bigger than 1 is going to diverge. Less than 1 is going to converge. So it's just like the geometric series, not the p-series. P-series is the oddball. All right, so all we do, it's going to look a little bit like the limit comparison test that we just did. You form a ratio and you take the limit. And then you analyze that ratio's limit. Now, the idea is pretty intuitive, actually. So if we look at taking the ratio of consecutive terms right here, if you do some expansion, say, okay, well, if we imagine we're out in the tail, then this is sort of what the tail looks like, okay? And if this limit exists right here, let's see, right there. If that limit exists, you can sort of think of this ratio as being equal to r when you're out in the tail of the series. Or we're dealing with the sequence here. When you're out in the tail of the sequence, this ratio is essentially equal to r. And if you multiply both sides by this a sub k plus 1, I didn't multiply properly here. I have this backwards. See it, don't I? Hold on. Oh, this is what I have backwards. That should be a sub k plus 1 over a sub k. You always are doing the subsequent term over the initial, over the prior term. This should be, I did these two backwards. Get in there, get in there. This should be a sub k plus 1 in the numerator. Yeah, okay. Then the math will work out. Okay. So as we get further out in the sequence, if this ratio is approaching r, it's like this ratio is equal to r eventually. And if you multiply both sides by a sub k, absolute value, you get that. That's geometric. When you have a term and you multiply by r to get to the next term, and you multiply by r to get to the next term, this tells us that the tail of this sequence is essentially geometric. And we know that a geometric series converges if r is less than 1. So this sequence up here, the a sub k sequence, is going to behave like a geometric sequence, which converts to a geometric series. The geometric series has terms that are from a geometric sequence. And this is going to act geometric in nature when you get out into the tail. And so that's how we get our conclusion. So the ratio generates something that's almost a geometric series, which is why it looks like a geometric series in its conclusions. So let's try it. Ratio test is best if you have factorials. We've seen so far that if you have factorials, a lot of times when you take limits, you just use growth rates. The nice thing about the ratio test, if you have factorials, is that the factorials are going to disappear. Now, one other point I need to point out, one other thing I need to point out. This limit is with an absolute value. So we're taking the absolute value here. So this a sub k could be positive, could be negative. We are going to force absolute value here. So we are actually going to be analyzing for absolute convergence. So here's what we're going to do. So we're going to take the limit as k goes to infinity of the absolute value of a sub k plus 1. It's always the next term over the prior term. So that. And so this will be limit. And we're taking absolute value so we can just ditch the switch. So this is going to be 2 to the k plus 1 divided by k plus 1 factorial. So that's a sub k plus 1. Dividing by a sub k means multiplying by its reciprocal. So we'll have that. And let's focus on the 2's first. How many 2's are left and where? So we've got 2's in the top, 2's in the bottom. When we cancel, how many are we left with?
1.
1, 2? And is it the top or the bottom?
Top.
Top. Everyone agree? All right, we got 1 extra 2 up there, so we're left with this. Now let's focus on the factorials. What's k factorial over k plus 1 factorial? So remember that k plus 1 factorial, we do repeated multiplication by subtracting 1. So isn't k plus 1 factorial k plus 1 times k factorial? Right. Just like if you had 7 factorial, that's the same thing as 7 times 6 factorial. Same idea. So what is the k factorial over k plus 1 factorial reduced to in the denominator? Just k plus 1. Yeah. That k factorial part of it is going to cancel. And what is this limit?
Infinity, or 0.
0. Yeah, 0. Because the denominator is going to infinity. So the fractions are going to go to 0. And now we go to the geometric series conclusion. We compare to 1. Is this less than 1 or greater than 1? Less than 1. And what's our conclusion? Therefore converge. Right? Geometric series less than 1 converge. So therefore we have, and we can be more specific and say absolutely convergent because we took absolute values. And we do have that theorem that says that any series that converges absolutely also converges regularly. So that series converges absolutely. Not too bad. A lot less work than some of those alternating series tests. All right, let's try another one. So this one, we have an exponential in the denominator. Let's see how it all shakes out. So absolute value of a sub k plus 1 divided by the absolute value of a sub k. So the limit of the ratio of consecutive terms. A sub k plus 1 is k plus 1 squared divided by 4 to the k plus 1. So there's a sub k plus 1. Absolute value. Oh, we don't even need to think about absolute value in this case because everything's positive already. So we get that. All right. So let's focus on the 4's first. I see 1 extra 4 in the denominator. 1 extra 4 in the denominator. I'm going to write that as 1/4. And I don't see a cancellation with these k's, but I'm going to group them together so that we have k plus 1 over k quantity squared. And can you tell me what the limit of all that is as k goes to infinity here? So what happens in here?
That just becomes 1.
This all becomes 1? So if you push the limit inside, the squaring function is a continuous function, so the limit can go inside those parentheses, and the limit of k plus 1 over k is 1, because the powers of k match. So we look at the ratio of leading coefficients, or you could use L'Hopital's rule, or you could divide by k. So the limit of this is 1, and 1 to the 2 is not indeterminate. 1 to the infinity is indeterminate, but 1 to the 2 is just 1. 1 times 1 is 1. 1 times a quarter is a quarter, so we get 1/4. And then we compare that to 1. That's less than 1, therefore converge. Now you could say absolute convergence, but that's kind of meaningless if everything's positive already. If everything's positive already, convergence and absolute convergence mean the same thing. So that's not too bad. Limit of the ratio of consecutive terms.
So when do we use the ratio test? Why do we choose to use that?
If you have factorials, ratio test is always the best test, because none of those other tests give us a way to analyze factorials. So if we have a factorial, we always use ratio test. But ratio test works more generally with polynomials and exponentials also.
Okay.
Like if we were to try another test, up here you could use the alternating series test. Right? And then but the problem with the alternating series test is that we would have to do the alternating series test 2 steps, and then we'd say, oh, it converges, so then we'd look at the series with absolute values, and we'd have to do a lot more work. But this we could cut to the chase really fast. Here, I can't think of another test that would work here. You can't use a comparison test. It's not a special series. So if you have something, it's sort of, if it's not a special series and it's not, then you can't integrate it. Like integrating this, you can't integrate that easily. A polynomial over an exponential.
Sure.
You could try to use integration by parts. If anything was going to work, it would be integration by parts. But it would be not pleasant. So ratio test is going to be, like when we look down here, choosing a convergence test, it's like if we have one of our 4 special series, then we're going to use those special things. If the sum and is easily integrable, we'll go with the integral test. If we have factorials, we're going to go ratio test. And then this can be used more generally also.
Okay. Okay, so if like 1, 2, and 3 don't work.
Yeah, exactly. All right, so let's try. I'll do one more and then I'll let you try the next one. So let's do one more here. So the ratio test is an absolute convergence test. So we're taking absolute values right from the start. So it's just going to get rid of the switch instantaneously. So the ratio test says to take the absolute value of the terms. So the a sub k plus 1, we're going to forget about the switch. Absolute value of the switch goes away. So here is a sub k plus 1, absolute value. A sub k, it's everything in here except the switch, and we flip it, dividing by a sub k, so we multiply by the reciprocal. K squared goes up top, 7 to the k goes down below. So we have that. And then, just like the last one, we compare these exponentials here. We have 1 extra 7 up top. These powers of k match. So we're going to have k over k plus 1 quantity squared. Now we can evaluate this limit. That limit is 1. So this overall limit is 7. We compare it to 1. That's bigger than 1. So what's our conclusion? Diverge. Which makes perfect sense because the numerator is an exponential, and the denominator is a polynomial, and so if we think about our growth rates, that numerator is going to infinity much faster than the denominator is. So that's going to drag the terms away from 0. So this one, another approach to this one would be the divergence test, which is something we should be thinking about all the time. Do the terms go to 0? And if we looked at this and tried to take the limit as k goes to infinity, we could use L'Hopital's rule 2 times and show that the limit is not 0. So that would also work. All right, you all tried this one with the ratio test. So if you see a factorial, that is your first instinct, is to go ratio test. So see if you can get it. Keep going. So you have the factorial piece will cancel out. They don't cancel. They're going to combine like we just did up here. They have the same power, so you're going to have a k over k plus 1 to the 6. Those will have some cancellation. Yeah, I'll write that k plus 1 factorial cancellation up here again. So yes, I've heard a couple of people say the right thing. When you form your limit, you've got that. The k factorial will cancel into this k plus 1 factorial, leaving just k plus 1. So that's k plus 1. And then the power of 6 thing, you're going to have k over k plus 1 all to the 6. This factor goes to 1. And you have 1 to the 6, which is determinant. 1 to the 6 power is 1. But then this piece right here, what's the limit of k plus 1 as k goes to infinity? Infinity. So this limit is infinity. And when we are dealing with the ratio test, infinity is greater than 1. If we look at the test here, so greater than 1, yeah, that diverges. So greater than 1, we're going to treat infinity as greater than 1. So that'll be divergent. So therefore, diverges. So if that is bigger than 1, diverges. So that is the ratio test. The root test is super similar. When we look at the root test, they use a different letter. They use R for ratio, and they use Greek letter rho, which also means R, but R for root instead of ratio. So they're using a rho for root instead of an R for ratio. It doesn't matter. You can call it R if you want. Some books just call it R. Because the conclusion is exactly the same. Greater than 1 including infinity. Maybe I should write that in the other slide. Greater than 1 includes infinity. So here, once again, we're going to take absolute values, but we're going to take the kth root of the kth term. We're going to take the limit of the kth root of the kth term, and then our conclusions are the same. The outline of the proof is really similar. If you're out in the tail, it's like rho is equal to the kth root of the absolute value of a sub k. So when you're far out in the tail, rho is approximately equal to that. If you raise both sides of that to the kth power, you get the absolute value of a sub k is approximately rho to the k. So in the tail, you have a constant multiplier of rho. So it's geometric, so you have the same conclusion that the geometric series would have. So root and ratio both mimic geometric series. When do you use the root test? When there's a big power on the outside. If there's a big power on the outside, the root test will take that thing away. So here's how the root test works. We're going to call it rho. We're taking the kth root, the limit of the kth root of the absolute value of a sub k. So once again, we're dealing with absolute convergence. And anything that converges absolutely, bless you, will also converge.
For the 1, 2, 3, they were the same as with the ratio test.
Identical to ratio test. Less than 1 converge, greater than 1 diverge, equal to 1 inconclusive. All right, so here, limit. K is going off to infinity. We're taking absolute values. So we're taking the kth root of the absolute value of a sub k, and the absolute value of a sub k is just going to take away that switch in here. So that minus sign in there is going to go away when we take absolute value. And then the kth root of ratio to the kth power is just the ratio. So we end up with 2k divided by k plus 1. And what is that limit?
2.
2. Got polynomials with the same degree. The limit is the ratio of coefficients, which is 2. This is greater than 1, which tells us diverges. Just like the geometric series. So root and ratio, less than 1 converge, bigger than 1 diverge. All right, we might have been able to show that this diverges using the divergence test also. It's a possibility. But when you see that k there on the outside, the root test is fast. Cuts right to the chase. All right, let's try this one. So here, rho is equal to the limit as k goes to infinity, the kth root of the absolute value of a sub k. All right, everything is positive here already, so we don't have to deal with taking away minus. And we're going to do the kth root of k to the k over 2 to the k. And that k, that should be sort of tucked inside a little better in there. So this is just k over 2. And what's that limit? Infinity, which we say is greater than 1, which tells us that we have divergence. When you look at that one, that should be obvious. K to the k is a power tower. That's the fastest growing function that we look at, and it's in the numerator. It goes to infinity much faster than an exponential, so it's no surprise that it diverges. But a lot less work than some of the other ones we've been looking at. Okay, so let's go on a little adventure for a moment. and look at the kth root of k. This is going to come up with this root test quite a bit. And so the question is, what is the limit of the kth root of k? And I've got the picture of the sequence kth root of k right there, and you can see that according to the picture, it's going to converge to 1. But it's not intuitive. This is what the sequence of terms looks like. You know, all the way through. You keep imagining 100th root of 100, 1000th root of 1000, and it's going to converge to 1. What do you think we would use to show this? How could we prove? Okay, we see a graph. It's like, okay, it looks like it's converging to 1, but how would we prove that that limit is 1? What technique have we used to analyze limits?
Limit comparison test?
It's not a test. So we use the test when we're talking about a series. But if we have a sequence and we're trying to find the limit of that sequence. So we had this technique that we use called the because we have to do something here. And this k is in the like you can imagine it as in the power, like k to the 1 over k. What do you do? How do you get a power to come down in front?
Oh,
Oh, you have
So we take a log. So we're going to use the log limit process. So let's do that. So if we say, hey, let's define y to be x raised to the 1 over x power, then we can take the natural log of both sides, and that natural log is what allows us to bring that exponent down. So we have that. Then we take the limit of both sides, and on the left, the limit can float to the inside because the natural log is a continuous function. And then on the right, we're taking the limit as x goes to infinity. And we're hoping for a L'Hopital. So we're going to push that x into the denominator, so now it's indeterminate. Natural log of x over x, both top and bottom go to infinity, so we have that indeterminate form, infinity over infinity. So we can use L'Hopital's rule. So I'll just indicate that that's infinity over infinity. So we take the derivative of numerator, take the derivative of denominator, and what is the limit of this as x goes to infinity?
0?
0. Numerator goes to 0. 0 divided by 1 is still 0. And now our goal is to isolate limit of y. Right, that's what we're trying to do. We want to find the limit of this function that we're calling y. And so what do we do to both sides? Exponentiate. And so that tells us that the limit of y as x goes to infinity is e to the 0, which is 1. So this is going to be one of the basic facts that you can use and not have to prove. So if you come across a limit of the kth root of k, you can automatically just write it's 1. You don't have to prove it unless the problem said prove that the limit is. Did I just hear something? Or was that in my head? All right, so let's take a look at this one. So we see a power of k down here. We don't see a power of k in the numerator. But now that we have at our disposal this extra fact that the kth root of k is going to go to 1, that's going to be very beneficial. So let's try. So we'll call it rho. That's what they use. So the kth root of k divided by e to the k. So there's going to be, there is our root setup. And if we distribute that kth root, we're going to have the kth root of k in the numerator, and in the denominator, we just have e. So what is this limit?
1 over e.
1 over e. The kth root of k, we now know, we now have this basic fact that the k through to k goes to 1. So this is 1 over e, 1e. Compare that to 1. Is that bigger than 1 or less than 1? Less than 1. It's about a third. And what's our conclusion for root ratio or geometric series? Less than 1? Converge. So now we know that this series converges there. Which again shouldn't be a big surprise because the denominator has an exponential, the numerator has a polynomial. Exponentials grow faster than polynomials, so those fractions should be going to 0 fast. So no surprise. All right, you all try this one with the root test. How's that one? Remember, you're taking an absolute value. There might be some thinking about that absolute value and how it affects that quantity, that a sub k. Anyone know what the absolute value of 1 minus 5k is? I know you can see that it's going to be negative, 1 minus 5k if k is 2 or bigger. It's definitely negative, right? Any ideas for what the absolute value of 1 minus 5k will be in this case? You could go down that road. It's simpler than that.
Plus 5k.
Say that again?
1 plus.
Close.
5k minus 1.
What did you just say?
5k minus
Yes. So if you imagine, just imagine two numbers like 5 minus 2 and 2 minus 5. Don't they have the same absolute value? 5 minus 2 is positive though, 2 minus 5 is negative. You just swap them, you'll have the same magnitude, but one will be positive. Right? So if you do 5k minus 1 instead of 1 minus 5k, same magnitude, but now it's always positive. So based on our k's being 1 to infinity. So this is what absolute value of it will look like. Absolute value of 1 minus 5k. So it's coming from this principle that this must be true. So once you see that, hopefully you can get the conclusion pretty quickly. In convergence or divergence?
If you didn't, you actually would get the same answer because it would be the same with yes, so conversion would get negative 1/5 things into which is not correct. Because you have a negative, it would be 1 minus 5k, so it's going to be over negative 1, which is
Anyone vote for convergence? All right, let's go with convergence. I believe you.
those are different statements.
I believe you. Should I believe you?
Minus,
Sure, why not?
so it's the same magnitude.
All right, so when we take this kth root of all of this, again, we're taking the kth root of the absolute value, so I'm just going to put that in right there. That is the absolute value of 1 minus 5k. When you take that kth root, that power vanishes, so you have the limit of k over 5k minus 1. And what's that limit? 1/5. and we compare it to 1, and our conclusion, just like the geometric series, less than 1 converge, bigger than 1 diverge. So therefore it converges. Now, just out of curiosity, if we just were thinking about the divergence test for a moment, if we were going to take the limit, just out of curiosity, so this is the divergence test analysis. Do you think we could calculate the limit of that using our shortcut? Like normally with a situation like that, we would go log limit. Log limit would allow us to pull that k down and use L'Hopital's rule. But we had a shortcut for log limit if it had a particular form. And remember that our shortcut was 1 plus a over x to the bx. What does that go to?
E to the AB.
E to the AB. So my question is, do you think we could manipulate that just to see if we could do a shortcut analysis? What happens if we flip the denominator? What would we do to the exponent? Make it negative, right? And then we could distribute in here, and we would have 1 over k minus 5, minus k. So, is this in that form? Is this indeterminate in that same way this is? What is the limit of this as k goes to infinity? Let's remember that the indeterminate form here as x goes to infinity is 1 raised to a power, right? 1 to the infinity. That's what's indeterminate. If it's 1 to the, is this 1 to the infinity? No, it is not. This part here is going to go to 0. So this base is going to -5, and the exponent is going to -infinity. So this is really, we can kind of ditch this part because we know that part's going to 0. So this really is a situation where if we push this into the denominator, we have -5 to the -k, so it's 1 over -5 to the k. And what is that limit? 0. Which we already knew had to be the case. If this series converges, the only way a series can converge, it's necessary that the terms go to 0. So this confirms that the terms are going to 0, so the dt would be inconclusive. Terms are going to 0. The question is, do they go to 0 fast enough? So it just has a look like some of that stuff that we've seen where we could use this to show divergence by divergence test. But this is just confirming that the limit's actually 0 and the divergence test is inconclusive. But it begs us to want to try to use that idea. But it doesn't work. Okay. All right. What do you think we're going to use? Which test will we use for that top one? As soon as we see that factorial, go to the ratio test. So try that. Let's see if you can figure out all the factorials that get jumbled in here all together in like a big old mess. Give it a shot. Corbin is missing. Henry. Richard. I'm going to write one little hint up here to make sure you're thinking of this properly. 3k factorial is 3k multiplied by 3k minus 1 factorial. Another thing I'll write up here is that 3, if you replace k with k plus 1, that's going to be 3k plus 3 factorial. When you replace the k with k plus 1, everyone tracking that? If you replace this k with k plus 1, it's all inside those parentheses, so it's going to be 3k plus 3 factorial. And what would that look like? If we expanded that, 3k plus 3, what would the next factor be? 3k plus 2, and then 3k plus 1, and then 3k factorial. So remember, your factorials are repeated multiplication by subtracting 1. All right, so whatever you have in your leading front parentheses, if you repeatedly subtract 1, that creates the subsequent factors. Bless you. Is everybody seeing that? Does that make sense? All right, we just repeatedly subtract 1 to get the subsequent factors. So you should see a cancellation. You're gonna write what you just said. Okay, so you're going to expand that. All right, so I'll write out at least the ratio first. Let's make sure you... So that's what your first step should look like. When you replace the k's with the k plus 1, that's what it should look like. So let's focus on the factorial piece with the k's here first. This one with the cubes. Let's write it like this and tell me if you agree that you could factor that cube out and you could treat it this way. So that is that. Everybody agree? Bless you. And then the 3k quantity factorial, when we divide by this 3k plus 3, we're going to expand it. We're going to make that 3k plus 3, 3k plus 2, 3k plus 1, and then 3k factorial. All right. So tell me what's left in this front part where the yellow is. What will we end up with here?
K plus 1.
K plus 1 to the third power. Okay. K plus 1 to the third power. And what about that second part? Doesn't that, actually, let's put this in the numerator, right? Because the second part's only in the denominator, the first part's only in the numerator. So k plus 1 cubed. Down below, this is canceling with this. So we have 3 factors down here. We have a 3k plus 3, a 3k plus 2, and a 3k plus 1. Okay. Now I've got to go back to what's that course? Calculus 1. We want to find the limit of this. Are you all comfortable with the idea that if you take the limit of a polynomial over a polynomial, it boils down to the limit of the dominant terms in the numerator and denominator? So this, what is the dominant term in the numerator? Instead of cubing out the whole thing, you know both these are polynomials. What is the dominant term in the numerator?
Is it a k cubed?
K cubed. Right? If you were to cube that thing out, you'd have a k cubed term, k squared term, k term constant. The only term that matters when you're finding a limit at infinity is the highest power of k. What would be the highest power of k in the denominator if you were to expand this all out?
27k cubed.
27k cubed. Right? It would be the leading term of each multiplied through. So that's going to give you the highest power of k is that first term. Right? 3 times 3 is 9, times 3 is 27. And then there'd be a whole bunch of other terms that are squares and linears and constants. But when you're taking a limit at infinity, the only thing that matters when you're dealing with polynomials are those 2 dominant terms. And what is this limit?
1 over 27.
1 over 27, which is less than 1, which tells us converge or diverge? Converge. Yeah. Make sense? So it's going to converge. So a lot of little bookkeeping things there with factorials. Any questions on how we got to any of these places? It's very easy to forget to distribute the 3 initially when you put in the k plus 1. So it's not 3k plus 1 factorial, it's 3k plus 3 factorial. Okay, this one, should we use root or ratio? Yeah, we have that power on the outside. We're going to go root. So let's go root here. So we're going to take the limit of the kth root of the absolute value of a sub k. Do we have any shenanigans? Do we have to do any manipulation with that base, the 1 minus 1 over k? Or is that always positive?
Yeah, that's always positive.
Yeah, it's never negative, right? When we plug in k equals 1, it's 0, but it's never negative, so we don't have to deal with any sort of absolute value manipulation. So when we take the kth root of all of that, we end up with 1 minus 1 over k to what power?
To the k.
To the k. The kth root, we have k squared times 1 over k, which is going to leave us with a single k right there. Now this one, we can use our shortcut limit for. This is e raised to a particular power. What power? Close. What is the coefficient of k up here?
Just
1. So the power should be e to the
-1.
just -1. So we're going to multiply the 2 coefficients. So the k disappears. We're just grabbing the coefficient of k in the exponent position and then that numerator. So this is e to the -1, which is 1 over e. And is that less than 1 or greater than 1?
Less than.
Yeah, that's less than 1, which tells us that we have convergence. That make sense? Aiden? I don't believe you.
E times B.
Don't believe you. All right, let me ask you a random question.
Should.
Let's suppose you have this series. A, does it converge? As it is, does that converge?
Yeah.
Yes.
Yes.
Why?
Because P is 1/3.
What kind of series is it?
Alternating?
Alternating.
Oh.
And remember that for an alternating series, we really have a shortcut process to see if it converges or not. All that has to happen is that whatever's not the switch goes to 0 in a decreasing way, then it's going to converge. So this is going to have regular convergence by the alternating series test, and intuitively in our mind, take away the switch, and that fraction goes to 0 in a decreasing way. So that's going to converge by AST. Now, does it converge absolutely or conditionally? Now we want to be thinking of P. So if we take away the switch, then what's true with this series? This is a P series with P equal to 1/3, which says diverge or converge? Diverge, right? So this is going to converge by AST. So what is that convergence, absolute or conditional then? Okay. So this gets classified as conditional. All right. Now what if we change this and look at -1 to the k, 1 over k squared? So as it is, alternating series, converge or diverge?
Converge.
Converge, because you take the switch away and the a sub k goes to 0 in a decreasing manner. Does it converge absolutely or does it converge conditionally?
Absolutely.
Absolutely, because this one, when we consider the P series, when we go to the series of absolute values, P is 2, which is bigger than 1, which is convergence. So this is going to converge by AST, and then we can classify that convergence as absolute because of the P series. So absolute convergence. Yeah. All right. Live long and prosper. Live long and prosper. See you Thursday. We have now completed all of the tests. You have all 10 of them. You have all 10 of them. If you have any questions, stick around. We can do more math. 2 hours and 15 minutes isn't enough. There's no need to rush off. 2 hours and 15 minutes. I'm going. Arctic monkeys. Were they good?
I love them.
Where did you see them?
It was at Red Wings.
Oh,
Like the best.
when was it?
It was in like 2023. It's been a while.
hoping like more of that sticks.
Yeah.
It's
Like,
also
Where did you see that?
Which is like.
that's what I'm hoping.
Oh, yeah, yeah.
And then this class.
My brother who lives in Seattle is Metallica fiend.
Yeah.
Loves Metallica. I've never seen them. No. We did go see some EDM stuff at Maxfield. That was.
Really isn't.
Do you see
I didn't even know what you
Yeah,
mean.
my kids are both into EDM. One of them especially is into EDM, so he dragged me and my wife
I think the
to
reason.
go
is
see
because it used to be an
Millennium at
online exam.
Empower Field. Is that where the Broncos play?
That was the
Yeah, it's
first
big.
time mine's got.
Yeah, Mile High. Mile High, yeah. It was crazy. So good, so fun.
University cheaters.
Concerts are fun.
That's my theory.
You awake?
I think so.
I think you were getting it today.
Yeah, I'm part of alternating. I'm always getting it, there's just too much to get.
You were tracking though, which is good.
Most of the time I zoned out at some point.
Stop.